There's three main parts that we're going to look at, beginning with the generalization of derivatives and problems involving derivatives to the multivariable case, and that is partial differentiation. The idea is, in a single variable case, you're computing derivatives using all the differentiation rules that you were taught, product rule, the useless quotient rule. So you have a function y equals f of x, and you apply these differentiation rules, what you're choosing, and you get the rate of change of y with respect to x. So what happens in the multivariable case? So now you have just an example of a function that depends on three variables, x, y, and z, corresponding to three spatial dimensions, and let's say the output is w. So there's no way to describe the rate of change of this function with respect to all of its variables using just a single number like we have here. Instead, all we could do with just one quantity is see how this function changes with respect to any one of these variables. So what you really get is, whereas here we have this that we call the derivative, and here what we have is called the gradient, and it's a vector quantity. It's a vector with three components because we have three variables. So this notation is used, so the upside down delta of a function, and the components of this vector are called partial derivatives with respect to each of these variables. So note the notation we use this symbol to indicate a partial derivative as opposed to the regular derivative. Now, how do we go about computing these? Well, we use the same differentiation rules as before. So in order to compute a partial derivative, the idea is you apply the differentiation rules with respect to one variable, whichever one you want the rate of change with respect to, x, y, or z, and then all the rest, you have to keep them constant. Let's suppose we have a function of two variables, f of x, y, x squared y plus y cubed. Partial derivative with respect to x, we apply these differentiation rules, treating it as a function of x, and y, we treat it as if it were a constant. So that means for this term we're going to have 2x times what we're considering a constant, y. And then for the other term, y cubed term, that doesn't depend on x at all. It only depends on y. So derivative of that part with respect to x is just going to be. And then df dy. So now we treat x as a constant, so we keep this part, x squared, and then differentiate to y with respect to y, and that's just going to give us 1. And then here this is just a function of y, so we differentiate that in the usual way. Okay. Now, we're going to deal with functions whose output is not a number, but a vector. So here we have what you could think of as a scalar valued function because it takes in three inputs, but it only generates one output. But suppose you have a vector valued function of, say, three variables. So it would have three component functions that depend on x, y, and z. So how do you describe a rate of change of this vector valued function with respect to three variables? Well, when we only have one output, we got a vector that describes the entire derivative. The three partial derivatives. Here, what we're going to have is actually a matrix. So the full derivative of f, as a name, is called the Jacobian matrix. And what we put in this matrix are the partial derivatives of all three of these variables. So down the first column, we're going to have partial derivatives with respect to x. Second column with respect to y. Third column with respect to z. So the columns correspond to what you're differentiating with respect to, x, y, z. The rows correspond to which component function you're acting on, f1, f2, f3. Here's some things that you are familiar with from single variable calculus and what you're going to generalize to multivariable case. So in the single variable case, one thing that you would have dealt with back in probably 167, coming up with the equation of a tangent line. So it would look like this. So it would involve the value of a function at a point, x naught, and the value of its derivative at that same point. This would be the equation of the tangent line for function f at the point x naught. So it's going to have the same function value, and it's going to have the same slope at that point. So if this is your f of x, here's your point x naught, that's your tangent line. That was then, this is now. Dealing with a function, say, of, let's just say two variables. Z is equal to f of x, y. Now what we have is a tangent plane, and the equation is going to have a similar form to what we see from a tangent line. So z is equal to the value of a function at this point of tangency, x naught, y naught, plus partial derivative of f with respect to x at this same point, and x minus x naught, partial derivative with respect to y at this point, y minus y naught. So in both cases, we have a difference of coordinates here, x minus x naught here and here, y minus y naught here. We have a derivative at this point of tangency. Here we have partial derivatives evaluated at the point of tangency. We have the function value at the point of tangency in both cases. Now, let's write this a little differently. So I'm going to take these partial derivatives and put them in a vector. I'm going to drop the x naught, y naught just because I'm writing enough as it is. And then what we have here is a dot product. So we have a dot product of this vector, which is the gradient of f at x naught, y naught, dot product with this vector, which I'll write as r minus r0. So what we see here is a linear approximation of a function. So we have our function, it's now a surface, and here's our point of tangency, so you can think of it being a tangent plane that has the same slopes with respect to x and y at the point of tangency. So this plane is a linear approximation of this entire surface described by f. Here, this r is just some point x, y. So what I'm doing here is, from the point x naught, y naught that's on this surface, we're seeing a change that depends on how far I wander away from this point of tangency and the partial derivatives. Based on the dot product, what would make this change as large as possible? I can pick x, y to be anything I want. I can make this vector any vector I want. What makes a dot product as large as possible? So if you have any old vectors, u and v, you take their dot product. What makes a dot product as large as possible? What will that be true of u and v? Yes, so this is equal to the magnitude of u, magnitude of v, if u and v are not only parallel, but are in the same direction, pointing with each other, whereas if we're pointing in opposite directions, then we'll just have a minus here. So, what that means is, if I choose to wander away from this point of tangency parallel to gradient, then we're going to have either the greatest amount of change possible, steepest increase, or the greatest decrease possible, so steepest descent, depending upon whether I'm going in the same direction as a gradient or the opposite direction. So it's the steepest change. All right, this is something that we don't have in the one variable case. X is only able to go forward or backward. Once you go to even 2 dimensions, you have infinitely many directions to choose from to study how the function is changing. And it's very important in certain applications to know in what direction from a given point is a function increasing or decreasing most rapidly, or in what direction is it not changing at all. That's also very important. Other things that you saw from the single variable case. Chain rule. So if you computed the derivative of a composition of functions, so you would get the derivative of f times the derivative of g. So there would be a multiplication of derivatives, and the thing that a lot of students mess up, unfortunately, is that you have to remember to evaluate this derivative not at x, but at g of x. But the point is, there's a multiplication of derivatives